Okay, and now we have the next speaker, Pedro Lima and Sequeira, numerical approximation of two-dimensional stochastic neutral field equation with finite transmission speed.
So first of all, I want to thank the organizers of this conference for this opportunity to participate. I must say that for me, I'm especially happy to participate in this conference, which takes place in the university where I studied in the years 80. It's a pity that I cannot be there physically like it happened 20 years ago when there was another conference in 2001, also dedicated to the great mathematician Petrovsky. But I hope that in the near future we will have the opportunity to meet again.
We also hope
in this in my alma mater in the MGU. So thank you, Irina, for organizing and giving this opportunity. The subject of my talk is a little out of the scope because it's not on a qualitative theory of differential equations. It's rather in the numerical approximation of an integral differential equations. And I must say that the results I will present, they were obtained with my master student, Tiago Sequeira, who is the author of the programs that were used to do the numerical simulations that I will show. So, first of all, the main application of the equation I am concerned with is the simulation of neural activity in brain. And I must say that the brain is perhaps the most complex system that science has tried to simulate. Actually, according to our estimate from 2009, the human nervous system contains about 0.89 multiplied by 10 to the 11 neurons. And these neurons are connected by about 10 to 14 synapses. So this is a huge system to simulate, and it has been a very big challenge for many scientists. Just a few words about the structure of the neuron. I think it will be useful for you to understand the equation I will present. There are many different types of neurons, but a typical neuron consists of three parts. One of the parts is the dendrite. The dendrite plays the role of an antenna which catches signals from other neurons. Then we have the nucleus, the central part where the information is processed, and the third part is the axon. The axon plays the role of a transmission cable. It's the cable the neuron uses to send signals to other neurons. So the transmission flow goes from the dendrite to the nucleus and then to the axon. So in the present slide, what you can see is how the electric potential of a neuron changes. So you can see that from time to time there's peak of potential. These peaks are called the spikes. So the spikes occur in the moment when the neuron fires. We say that the neuron fires when it sends a signal to other neurons. So in a certain sense, the neurons communicate between themselves by firing. Okay. And so now I present the equation, which is the main subject of this work. It's called the neural field equation, and it has been used since the middle of the years 17 or in the last of the last century. It's an integral differential equation. Here, the unknown function is the function v, which is a function of the spatial coordinates x and the time, okay? The problem is posed on a certain domain omega, which can be one-dimensional or many-dimensional. In the examples that I will share with you, I consider both one-dimensional and two-dimensional case. So a little about the physical meaning. As I already said, function V is the electric potential. Then we have this function I, it's called the external input. It's some external stimulus that excites the neurons. It may be a sound or an image. And then this integral here plays a very important role because it represents the summary interaction between all the neurons in domain omega. It is composed by this function k. It is known as the connectivity function. So it gives the strength of the connection between neurons at places x and y. And this function S here is called the firing rate. It represents the capacity of the neurons firing as a function of the potential. So it is known that a typical neuron can send signals only if the potential V is above a certain threshold. This function S can be, for example, a Heaviside function. So it is 0 when V is less than the threshold, and 1 when V is greater or equal to the threshold. This is the simplest model, but there are more sophisticated models when sigma is a continuous function of sigmoidal type. So as I already said, the domain omega is a domain in R D. D is the dimension. So in the case D equals 1, it's just an interval. In the case D equals 2, it will be a square with the center at the origin of coordinates. And we are simulating the equation in a certain time interval 0, capital T. As I already said, I is the external input and K is the connectivity between neurons. Okay, so in many applications, the neural field equation is not enough to describe the essence of the process, because in the neural field equation, as I showed it before, don't take into consideration transmission delay. What is the transmission delay? Is the time needed by the signal to reach the point Y from the point X. In this new version, which is called the delayed neural field equation, we have a delayed equation where D represents the transmission delay. So it's very important for some phenomena, for the description of some phenomena, it's very important to take into consideration this delay. And we just assume that this delay is the quotient between the distance between neurons and the transmission speed V. So V here stands for the transmission speed, which we consider constant. Okay, so Another point which is important for this model is that we want to take into consideration the effect of noise, because many of the problems that I will show in the numerical examples were studied before in the deterministic case, but here we want also to analyze noise-induced changes in the behavior of the solution. This is why we consider this stochastic variant of the neural field equation. This stochastic version was introduced in a paper by Kuhn and Riedler in 2013, and we took it as the basis for our numerical model. Our numerical model is based on this equation. So here W is a Wiener process which represents the noise. And epsilon, we will mention frequently this parameter. It is the parameter which gives the level of noise. So epsilon is 0. We are back to the deterministic case, and as we increase epsilon, we increase the level of noise. Okay, so when we have simultaneously the neural field equation with noise and with delay, we get this last equation, which is the subject of our work, the stochastic neural field equation with delay. As I said, our work was a numerical investigation. So we will show. I will show you numerical results. To obtain this, I will give now an outline of the numerical method. First, we search for the approximate solution in the form of a series where phi mn are the basis functions. I will describe them in the next slide. So we are looking for the coefficients Vmn, the Fourier coefficients of this series, and the series, of course, is a finite series. M and N are certain positive numbers, our aim is that as M and N tend to infinity, the approximation solution converges to the true solution of the equation. So our basis functions we have chosen as trigonometric functions. Why? In this way, when we have to compute inner products in our algorithm, the inner products can be seen as Fourier transforms, and then we can use the fast Fourier transform, which is very important to reduce the computational cost of the algorithm. Okay. And we are applying the Galerkin method. This means that we take the inner product of each term of the equation by the basis functions phi mn, the trigonometric functions. So we transform the original equation in this system of stochastic equations. Okay. And we, as I said, for the stochastic version of the equation, we are following a paper by Kuhn and Riedler, who also show how to expand the stochastic term. The stochastic term is expanded as a series of the eigenfunctions of the covariance operator. The functions Fmn, as known, form an orthonormal system of functions. Of course, for our numerical method, we need to introduce discretization in time and in space. For the discretization in time, we use uniform mesh of step delta t, starting at t0, which usually is 0, and the last point of the time interval is capital T. We have nt steps in time. For the spatial discretization, we also consider a uniform mesh on the square with a step size delta x in the x-axis and a step size delta y in the y-axis. This is, of course, for the two-dimensional case. In the one-dimensional case, we have only delta x. So, as we apply the Galerkin method, the original equation is reduced to a system of stochastic differential equations. And then to solve each of these stochastic equations, which has this form here, to solve each of these equations, we use the so-called Euler-Maruyama method, which is standard method for this for stochastic differential equations. It's a generalization of the Euler method to the case of a stochastic equation. I must say here that in terms of computational cost, the main computational effort is the computation of these coefficients A and N here. These coefficients result from the integral operator, and if we would compute them straightforward just by numerical quadrature, this would take too much computational time. So it's very important that we use the fast Fourier transform to approximate these integrals. Once we solve these stochastic differential equations, the solution V at the time moment ti plus 1 can be obtained as by an inverse Fourier transformation. So Vmn hat are the Fourier coefficients. By the inverse Fourier transformation, we have the value of the solution. So this is the outline of the numerical algorithm. I wanted to say just a few words about convergence and complexity. As I already said, the integrals are approximated by inner products, and this corresponds to a discretization error of the order of delta x, of the discretization step in x. On the other time, use the Euler-Maruyama method, we have first order convergence of first order convergence in time. So the overall convergence is of first order in space and in time. Now, as I already said, it's very important that we use fast Fourier algorithms to approximate the integrals, because when we use the fast Fourier algorithms, the complexity is n to the d, where d is the dimension. For example, in the two-dimensional case, the complexity will be n squared multiplied by a logarithm. If you just use a straightforward method, just to use quadratures to compute the integrals, the complexity would be twice higher. It would be 2n to the 2d. Okay, so this is why I underline that we are using the fast Fourier transform. And now I will present the results of some numerical simulations obtained by this algorithm. I want just to remark that when we use the stochastic equation, our results present the mean solution. That is, we compute 100 realizations of the stochastic process, and we divide by 100, so as usual. And the other coefficients are the dissipation coefficient alpha is 1, and the correlation coefficient is 0.1. So these first two numerical examples are, I can say, academic examples. So these are examples where we know the exact solution. It's not typical. Usually we don't know the exact solution, but we have these two artificial examples just to test the performance of the method. In the first example, we have the external signal I equals 0. Then we have a connectivity function of this type. It is sometimes called the wizard hat. It's because it has a peak at 0, where the function is not smooth. And the firing rate function is of the simplest form I've mentioned, the Heaviside function. So the firing rate is 1 if the potential is greater than a certain threshold, and is 0 if the potential is less than this threshold. In this case, it is known that the exact solution V1 is of this form. So we can compare the numerical solution with the exact solution. And in this case, the solution does not depend on time. It depends only on the spatial coordinates x. So we use this example to test the convergence in space. The second example is used to test the convergence with respect to time. So in the second example, we also know the exact solution. The exact solution in this case is exponential of minus t. So it does not depend on space. So we use this example to test the convergence with respect to time. Now, in this slide, you can see two tables which are with the results of these two examples. In the first table, we are just changing the step size in space, delta x, and we see that when we reduce 2 times the step size in space, the error also reduces about 2 times. And in the right-hand side, we can see an analogous experiment where we change delta t. So if we reduce delta t to 1/2, we also, the error also reduces approximately 2 times, okay? So these examples, as I said, were just to test the numerical method. Now we'll see other examples which are more interesting, which are related with some real-world phenomena. This example, for example, which we call just 1D bump, this example simulates working memory. So what is working memory? Working memory is the capacity that the neural fields have to conserve the information resulting from a certain external signal. The external signal is represented by this function I, So what is typical in this example is that the external signal is active only during the interval time interval 0, 1. For t greater than 1, we have no external signal. The function y has this value, which is just the resting value. And the connectivity function in this case is an oscillatory function, so it decays. It decays exponentially, but it has oscillations resulting from this part here, and what we can observe in this example, in the first time t equals 0.6, this is when the input is still active. We have a solution which is here in blue. The blue line is the solution. It reflects the external signal which is still active, and when t equals 1, is the last moment when the input is active. We still have a solution with the same form. Then, as the input has ceased, what happens is that the amplitude of the solution reduces, but it does not go back to the initial state. So even after the input has ceased, we have a stationary solution which reflects the properties of the external input. So this is what we call the working memory. The neural field retains the information about the external signal when this signal has already is already turned off. In this example, we have considered both the case of finite speed, is the case the line in blue. So finite speed is when we have the equation with delay, and the case of infinite speed. If we do not consider delay, then the solution is represented in green. We see that in the first moments there is a difference between the two solutions, but then as t tends to infinity, the two solutions are very similar with finite speed and infinite speed. Now, the same example, but with in the stochastic case. So here we want to show the effect of time. And a question that is very important here is, will the effect of noise modify the stationary solution? In the deterministic case, we have seen that the stationary solution has the same profile, the same qualitative behavior as the external input, which is in this case is characterized by one bump. Yes, we have just one bump. What we see here is that if in the stochastic case, if the the noise is strong enough, and in this case the noise is characterized by epsilon equals 0.05, in this case the response of the neural field has a different profile. In case instead of one peak, it has 3 peaks. So this deformation is a consequence of the noise. Now, so far I have only presented one-dimensional examples. Now we have a two-dimensional example where the neural field has a typical symmetry. We call it hexagonal symmetry. I will show you why. Again, in this case, the external input has the form of a Gaussian function, but in this case it is constant, so it does not cease. It continues through the whole time interval. The connectivity function K is also oscillatory and decaying to zero at infinity. But because of these coefficients Kg here, they have it has the so-called hexagonal symmetry, which then reflects in the solution. The firing rate in this case is not Heaviside, it's a sigmoidal function. So we also have here a threshold 3, but the function S is smooth. It varies from 0 to 1 continuously. The initial condition is given by this value here, 2. We say that this value is the resting value of the field, and it's very important that in this case we are considering delay. So the initial condition is given in the time interval of minus tau max to 0, where tau max is the maximal value of the delay. So the maximal value, as you can imagine, depends on the size of the domain and on the propagation speed. Okay, so what we can see now in this video is how the neural field changes with time. Initially, the neural field is 0, and then it spreads along the domain. And what we can compare here is how it spreads in the right-hand side and in the left-hand side. In the right-hand side, where the velocity is 80, it spreads very fast, as we could expect because of the higher velocity. While in the left-hand side, the neural activity spreads much slower. Okay, so it's the aim of this example was to simulate the importance of delay in this neural field. But now it's just the deterministic case. In the next slide, we'll see the effect of noise. So here, now we have just a snapshot at a certain time moment, at the time 0.45. And in the case of the finite velocity 10, v equals 10. The picture here is not very different from the deterministic case. Well, the deterministic case would be with epsilon equals 0. Here, the level of noise is low, just 0.01. And what this picture shows, the central circle is a high peak that reflects the external signal. And then, as you see, we have other blue circles which represent smaller peaks, and these smaller peaks form hexagons. This is why we call this hexagonal symmetry. They form hexagons around the central peak. So here, with the external, with the level of noise 0.01, we have picture which is not very different from the deterministic case. In the next slide, I will show you what happens if we increase the level of noise. Here, at the time 0.5, with noise equals 0.05, so the level of noise here is 5 times higher. And what we see is that we obtain different patterns. For example, at time 2.5, we still have certain marks of the circles surrounding the central circle, but with time these circles disappear, and instead of them we have these strips which remind Turing patterns. So the effect of noise has destroyed the symmetry that we had in the deterministic case. Here also we can see some 3D graphics where you see the deterministic case epsilon equals 0 when we have this very clear symmetry. We have the central peak and then smaller peaks around it. Then with a small level of noise, we still have a similar picture. And then as the level of noise increases to 0.05 and 2.1, the symmetry disappears. In the case of epsilon equals 0.1, we have just random fluctuations in the neural field. Okay, and finally, I would like to present an example of a different type. It's what we call a breather. A breather is a neural field with oscillations which are limited in space. So we have a certain part of the domain omega where we can see oscillations, and we will see that in certain cases these oscillations approach to certain stationary solution, but in other cases they just keep oscillating. We have a pure oscillatory solution. In this case, the external signal again has this form, the form of a Gaussian function, and the connectivity function is what we usually call a Mexican hat. So it's the combination of two Gaussian functions. This gives that in the center of the domain we have positive connectivity, but then at a certain distance we have negative connectivity. The firing rate function here is a Heaviside function, and the initial conditions here is just 0. So we have the resting solution which is 0, and again here the finite transmission speed plays an important role. So we are considering a model with delay. So in this first example, what I see just for comparison is the case if there is no delay. If there is no delay and we consider the deterministic solution, the solution is just smoothly tending to the stationary solution. Stationary solution is this peak. So we after a finite time, the solution of the neural field reaches this stationary state. Okay, this is in the case of infinite velocity if we don't consider delay. Now we can see here the graphics which show the evolution in the case of different propagation speeds. In the case of propagation speed v equals 5, we see that first the field has some oscillations, and then it reaches the stationary state. And in the case v equals 3, we have the same situation, but the oscillations stay for a longer interval of time. Okay, this is as we could expect, as the velocity reduces, we have a longer interval of oscillations, and we will see this now in the video. Okay, in the right hand side, we had a lower velocity, so the field keeps oscillating for a larger interval of time when the field on the left hand side has already reached the stationary state. Okay, so we have oscillations in both cases, but in both cases, after a certain time, we reach the stationary state. And finally, now we are considering the velocity v equals 2. And in the case of such velocity, in our numerical example, the field keeps oscillating on the whole interval. So the oscillations are not damped. They continue over all the time interval considered. This suggests that between velocity 2, which is in this slide, and velocity 3, which was in the previous slide, we have a bifurcation point where the qualitative behavior of the solution changes. It changes from the stationary state to a pure oscillatory solution. Now, what to finish, the question we want to answer is, will the noise affect the bifurcation point? We will show this with a table. In this table, we have 3 different levels of noise. Epsilon equals 0 is the deterministic case. Then we have a small noise 0.0005 and noise twice bigger. And what on the other hand, we have the velocity, the propagation velocity, which is increasing. And what we can see is that for each level of noise, we have a bifurcation point. In the deterministic case, as we have already seen, the bifurcation point is between velocity 2 and velocity 3. In the case of noise, we also have a bifurcation point, but this bifurcation point will be at other values of the velocity depending on the noise level epsilon. Okay, so this is what our numerical simulations have shown. And now I want just to remark that the solver, which was written by, as I said, by my student Tiago Sequeira, this solver was written in the language Julia, which has become very popular in the last years because it has almost all the features that other languages like MATLAB have, but it's a free, it's a free language, so everyone can use this language without needing any license. And after writing this code for neural field equations, it was submitted and it was accepted to the library of Julia, so now it can be used by anyone. You here have the link that can be used to access this program. And so this is everything. I just want to thank you for your attention and to wish everybody a very happy new year. So if you have any questions, please.
Okay, thank you very much, Pedro. It was very interesting, unusual for our section, but we have not the first talk on the neural nets. So thank you. Maybe somebody has questions.
Можете ставить вопросы по-русски тоже. Я тоже понимаю, я говорил, я выступал по-английски, но я готов тоже ответить по-русски, если...
I listened his talk 1 year ago, and I think that you move quickly in studying this topic. Okay, so thank you for your interesting talk.